Hi everyone. In today's class, we're talking about work, energy, and power. So I'm going to start with what work is. Now, the reason we are taking all this, the three of them together, is because most like they are generally like interrelated. Which one do I talk about them? Like for example, now work is same as energy. Work done is the same as energy. Just like a different form, like a different way of actually like viewing it, basically. So we start with what is work. Now, work is is more like what you do. Like you have a force, you're applying a force to actually do something, yeah. So that something that you're doing is now work. Like you have an energy already stored in you. Like when you hit, you are gaining energy. You are more like storing up energy. So when you now expend that energy to do something, that's something that you are doing. That process is called what we call work. And the formula for calculating work is force times the distance moved by the force that you just applied. You're going to apply a force, and then the force is going to move the object in the same direction as the force that you're applying. So take note of that in order for you to calculate work, the work is equal to the force that you are applying times the distance moved in that same direction of that force. What that means is you can have something like like you have an object. Now you're trying to move it, this is the direction of your force. Now the work done, let's say you move this object now from here to here, this is D. So your work done is what? Force times distance moved in the direction of the force. But then assuming you apply the force in this direction and then the distance moved was now like this, you cannot, that's not, you did not do any work. You are just wasting your force. You're not doing any work. So that's what it means. So your work done is what? Is the product of the force that you're applying times the perpendicular distance. I said perpendicular times the parallel distance. Now the one for perpendicular distance is the moment, and moment is not work done. So don't mix both moment and work done together. Moment is the work. Moment is the product of the force applied and then the perpendicular distance. While work done itself is the product of the force and then the parallel distance moved. Parallel distance moved in the direction of the force. So that means both the force and the direction in which the object is being moved must be the same in the case of force. And in the case of work done. Okay. And another relationship you have is what? F cos theta. Like this is more like tails back to scalars and vectors. So when we solve questions in class, I will definitely emphasize on this and use a question to just emphasize on this. So take note of the fact that is what parallel the force must be in the same the distance must be in the same direction as the force, and for it to actually do any work at all. Now the unit of work done, the unit of work is joules. The unit of work is joules. Force times distance times parallel distance is what? Is joules. So the unit of work is joules. And the SI unit is now what? Kilogram per meter, kilogram meter square per second squared. So you can pause this video and attempt this question. Just briefly pause this video and attempt this question. Oh, you already have the answer there. Okay, you can just like go through these workings and then you see. Now let's talk about energy. Now energy is what you expend. It's more like work done is more like extrinsic. Energy is more like intrinsic. It's more like the stuff that you expend on actually doing a work. That's your energy. Is the energy. Energy is more like what you actually expend to actually do a work. Energy is the ability to perform a work. It's like something that is intrinsic. Where work done is what you are doing. It's like on the external, something that you can actually see that you are doing. While most people will know that you are expending energy. You are the only one that will know, oh yeah, I'm expending energy, because it's not like intrinsic. And you have different types of energy. These are the different types of energy. Different forms of energy as well. And the unit of energy is also work. It's also joules. It's also same as work. It's also joules. So that means that you can relate work done to what? To energy transferred. So when you are doing a work, you are transferring energy from yourself to the system that you are actually working on. So these are the types of energy that you have. You have mechanical. Now under mechanical we have what? Potential and kinetic. So you have chemical, electrical, magnetic, radiant, nuclear, ionization, electric energy, gravitational energy, etc., etc. And then what is now power? Let's now go to power now. The formula for calculating energy. There are different formulas for calculating energy depending on the type of energy you are dealing with. For example, now for mechanical energy, when we are talking about kinetic energy, the formula for calculating kinetic energy is half mv squared. While the formula for calculating potential energy depends on that kind of the type of object that you are talking about. You can have mgh, which is mass times gravitational constant associated to gravity times the height, depending on the object that you are talking about. And at the same time, you can have more like a spring now, an elastic spring of half ke squared. So you have different formula for actually calculating different potential energy of different objects. For elastic energy, that's half ke squared that I talked about. For elastic energy, you can use that for half ke squared. Now, what is power? Okay, you know what? Let's go back to work done. Now, when you want to talk about work done, now you have an energy. Let's say I'm running at a particular speed. So that means I have kinetic energy. Yes, I'm not specifically talking about mechanical energy now. That means I have this particular energy. So what that means is, as I'm walking, let's not say I now hit someone along the line. Now on hitting that person, the person will definitely feel something. That's some of my energy have been transferred to the person. The person will either more like a roll, or the person will start moving as well. So the person will gain some of my kinetic energy. Why me? I will lose some of my own kinetic energy. So indirectly, I've done work on that person. So that's the whole. So basically, work done has to do with transfer of energy. Work itself is just you doing something, while the work done itself has to do with you actually transferring the energy in you. The work actually doing transferring the energy in you to someone else. So that's more like work. That's basically the concept of like work done. I just really want to like talk about most of these major aspects, all these related concepts. Now let's talk about work energy theorem. As I said before, that work done is almost same as what energy transferred. So there's a relationship between them. Now what that says is, let's state the work energy theorem. Now work energy theorem says, so we now, according to work energy theorem, the net work done on a body is equal to the change in the kinetic energy of that body. Now this statement is not entirely complete, because work energy theorem says that the change, more like the net work done on the body, can either appear as either the kinetic energy or the potential energy. So imagine if it was not like a kinetic energy, it was not like I was running, it was like I lifted the person up. Now I'm expending energy for myself. I'm doing work, and I'm expending my own energy to the person. So the person gains potential energy. So it can either appear when there is a work done in the system, it can either appear as kinetic energy. It can either appear as kinetic energy or as potential energy. So that's basically what the work theorem is. So you can write this equation for work energy theorem. So you have something like this. You have work done. So you have work done to be equal to Ke, kinetic energy, plus potential energy. So you have that. So that's basically work energy theorem. Okay. Now let's go back to our energy. So let's talk about the different forms of energy. So as I said, you have heat energies. You are still going to talk about thermal physics later on. You have heat energy, you have chemical energy, you have electrical energy. I'm just going to talk about electric fields. You have nuclear energy, you're talking about nuclear physics. And there's a relationship between mass and energy. And that relationship is what? E equals to what? MC squared. We're still going to talk about all this under modern physics. Okay. Okay, now let's talk about the types of energy. Ah. Let's talk about the types of energy now. So the types of energy, you have all this kinetic energy and then the potential energy. The formula for calculating kinetic energy is what? Half mv squared. Because the kinetic energy relates your speed to your is related to your speed. Basically, we only have kinetic energy when you've gained speed. While potential energy is related to the position of the object. When the position of the object changes or increases, then your potential energy will increase. Okay. Now, law of conservation of energy, very important. Thank God I didn't miss this. Now, what the law of conservation states that in a closed system that is isolated from surrounding, the total energy of the system is conserved. So what this means is like the whole universe is it's not like an isolated system. So energy is neither lost nor created. It's only just what converted from one form to another. Basically, that's what the law of conservation of energy. Basically, just saying that energy is never lost. It's just being converted from one form to another. Basically, that's what the law of conservation of energy says. So you don't need to even cram. Just that in an isolated system or in a closed system, energy is neither lost nor created. Just put that at the back of mind. You don't need to like start saying, "Oh, the energy says that in an energy system." You don't need to like start wasting your energy. Just know the basic concept of that. And this law of conservation of energy can be traced back to that work done theorem, work energy theorem that I just described. Where you are doing work, so that work is not just going to waste. It's entering into the system and is being used to do. It's being used to like increase something. It's actually going somewhere. It's not increasing the kinetic energy or the potential energy of the system. Basically, this is basically about work energy theorem. So if kinetic energy is zero, that means the work done you are doing is if kinetic energy is zero, that means the work done that you are doing is going straight to the potential energy. While if the potential if work done is zero and then it is the potential energy that is being, let's say we are like a fruit now that is on top of a tree, then it fell down. Initially it has the potential energy, yes. Now it's not using that potential energy to be converted to a kinetic energy because it's going to gain speed as it's going downwards. So that's basically, just know your work energy theorem and then you are Gucci for law of conservation of energy. Now what is power? What is power? There's one of my classmates that is bearing power. I don't know if he understands what power is. Now power is the physical concept. Now basically power is the rate of doing work or the rate of energy transferred. That what that means is what determines how powerful you are is how much work you can do per time. Like the rate at which you can actually do those work is what determines whether you are powerful. Someone else might do the work like someone else might do the work, but then it might take them longer time. They are not that really strong. They are not really that powerful. But then if you are doing the work that takes close to like 100 men to do, you are doing it like in a very short period of time, and that means you are a very powerful person. So that's basically what power means. It's just like the amount of work per unit time, the amount of work that you can do per unit time. And the formula is what? Work done over time, or what? Energy transferred per unit time. Energy transferred over time. Now the unit of power is what? Is watt. The unit of power is watt. Now so there are some of the questions. You can attempt them. You can just go through them just for a better understanding. So I think that's all for work, energy, and power. So this is an overview. So you can just go through this. You can pause the video and go through this just to remember some of the important stuff. Okay. Okay. So that's all for work, energy, and power. See you guys in my next class.